Dear students, in this module we shall study about the substitution accompanied by the double bond shifts. After studying this module, you shall be able to know how electrophilic substitution reactions are accompanied by double bond shifts. You shall be able to learn the various methods of double bond shifts which are accompanied by substitution and identify the substrates that are likely to undergo these double bond shifts. You shall also be able to evaluate the role of different functional groups to facilitate the double bond migration through the electrophilic substitution, and you shall be able to analyze the stereochemistry of products formed on double bond migration. So, let us begin with some introduction, that is, when substitution reactions are carried out at an allylic substrate, the product may get rearranged based on thermodynamic stability of the intermediates and products. Some of this you are already aware with in your earlier classes. We shall go into more detail in this module. Such reactions are possible with nucleophilic substitution as well as electrophilic substitution. In an electrophilic substitution on an allylic substrate, on the attack of an electrophile, a displacement of double bond occurs leading to the product, as you can see in this visual. So, here in this equation you can see that Y plus is the electrophile and this X is at the allylic position, and as a result this X is getting replaced not at its original position but at the rearranged position. The mechanism of such substitutions can take two different paths. In the first pathway, when the substitution takes place by SE1 mechanism that you are already aware in the earlier modules, the leaving group leaves first, that is, it will lead to an intermediate carbon ion which is resonance stabilized due to an adjacent double bond, which is then later attacked by the electrophile, and this you can see in this equation as shown here, that is, you are having the X at the allylic position and this X goes out as X plus, this is the leaving group, and as a result you get this carbon ion, and you can see these are the two resonating structures, and because of this resonating species both these C minus can be further attacked by the electrophile, and so when the attack happens at this rearranged position, this carbon ion, as you can notice in this case, then you get the rearranged substitution. In the alternate mechanism, the electrophile is first attacked by the electron rich pi bond, leading to the formation of intermediate carbocation, which then loses the leaving group, giving rise to a double bond at the adjacent position. So, what happens in this mechanism, as you can see here, that shown here, this is the double bond, and at the allylic position this is the X. Then this double bond is attacking on the electrophile, which is Y plus here, and as a result we get this carbocation, and then from this carbocation you can see there will be loss of X plus and formation of double bond between these two carbons as is shown in this product. So, these are the two alternate mechanisms, that is, in first case the leaving group goes, there is a formation of carbon ion which undergoes rearrangement, and then it is attacked by the electrophile. The other mechanism where the electrophile is attacked by the double bond and leading to a carbocation, this carbocation will be then followed by the removal of the X plus the leaving group and resulting into a formation of a new double bond at the rearranged position. So, the groups adjacent to allylic system, if we go into the stereochemistry, they will influence the stereochemistry of the products to a great extent, and you can see this in this particular table as shown here, that the experimental data on the stereochemistry of products which is obtained using the specific substrate where the reaction is carried out at 55 degrees centigrade in DMSO as solvent with 0.77 molar olefin and 0.70 molar potassium tertiary butoxide as the base. So, all this data you can see is given here, and this we can compare in the first case where you are given this 1-butene as the starting material. The ratio of cis to trans when it is, that is the kinetic control, it is 47.4, and the ratio of cis to trans when it is thermodynamic control, it is 0.25. So, here you can see that the cis is higher. Going to the next one, we are having this 1-pentene as the substrate. The ratio of cis to trans is 10.8, that is kinetic control, and it is 0.23 when it is thermodynamic control. Moving to this substrate, here you can see it is kinetic control, you have 3.2, and thermodynamic control it is 0.23. Similarly, going to the next one, it is 0.25 and it is less than 0.001. And as you can see from this table, what you can notice is that all these alkenes are terminal, the double bond is at the same position, but at the allylic position, in first case you have the methyl substituent, in second you have ethyl, next you have isopropyl, and then you have the tertiary butyl as the substituent. And if you look at the order of kinetically controlled cis product formation, it decreases in the order of, that is methyl is greatest, followed by ethyl, then followed by isopropyl, and then followed by the tertiary butyl group. And initially as T approaches to 0, the cis alkene product dominates in this reaction. The predominance of kinetically controlled cis product has been retained under different solvent conditions and with different bases. When the olefin is substituted with an electron withdrawing functional group such as ester or carboxylic acids or ketones, then the geometry of product is largely trans, and this can be seen in this particular example as you can see here. So, shown here is the R group which is at the allylic position, and you can see that these two products, one is the cis and the other is the trans, and if we look at the nature of R, when R is COOET as the electron withdrawing group, then the cis is 15% and the trans is 85%. But as this R then goes to COOH, cis is 6% and R is 94%, and when R is COET, which is even more electron withdrawing than the earlier two groups, then cis is almost negligible, it is 0, and trans is 100% exclusive product. So, this means that as you have better and better electron withdrawing group, then the formation of trans product is going to be more favorable. The trans products, however, are more stable thermodynamically, and therefore ultimately if long isomerization time is provided, that is T approaches to infinity to the reaction, then the trans alkene product may become the major product. So, if T approaches to 0, that is for less duration, the kinetic product will be more favorable, and when more time is provided, then thermodynamic control takes place because the more stable trans product will become more major. Now, after this initial introduction that how this rearrangement happens and what is the effect of these different groups, let us see how the mechanisms of double bond shifts they take place in a detailed manner. So, first of all, let us try to understand the base catalyzed mechanism for the double bond shift. In unsaturated compounds, a strong base like NaNH2, alkali metals, KOH or potassium tertiary butoxide can snatch a proton from the sp3 hybridized carbon atom adjacent to a double bond, leading to the formation of a carbanion, which leads to equilibrium mixture of product isomers upon substitution. Historically, the base catalyzed double bond rearrangement was reported as early as 1892 by Griner et al., where heating of 1,4-hexadiene at 100 degree centigrade in the sealed tube in the presence of concentrated alcoholic QH led to the formation of 2,4-hexadiene. For such rearrangements, preferences were evident for formation of a double bond which may extend conjugation with already present double bonds if any. It was also observed that terminal alkenes isomerized to internal ones and the non-conjugated alkenes isomerized to conjugated alkenes, and similarly the exo 6-membered ring alkenes, they isomerize to endo-alkenes. And if you look at the mechanism of base catalyzed electrophilic substitution on allyl system, it consists of these two steps. That is, first step, as you can see here, you are having this alkene and at allylic position you have R, and with the base will abstract the proton from the allylic carbon, giving rise to this carbon ion, and this carbon ion can undergo rearrangement at this terminal carbon. And in the next step, that is step 2, what happens is this carbon ion will be further attacked by BH plus, and as a result you have the formation of this product. And here one more thing to notice is when this R is shown with a wavy bond, it is represented that both the cis and trans geometrical isomerism is possible here. So, we get this product which is R attached to this double bond and then further this CH3. So, notice that here the proton has been taken by the carbon ion at the terminal position, and that is why we are getting this rearranged product. If we consider an example, base catalyzed isomerization of allylic alcohols give rise to formation of ketones as the major products. So, as you can see here, this given molecule having a double bond at OH at different positions, how this isomerization is happening. You have this phenyl attached to CH double bond CH, and then further you have CHOH and phenyl. When it is treated with alcoholic QH for around 100 degree centigrade for 3 hours, what happens is this double bond which is earlier conjugated to phenyl now gets isomerized or rearranged to this position between these two carbons and results in the formation of enol, and this enol will tautomerize to this keto form which is the major product. In addition, partially intramolecular base catalyzed double bond shifts also have been reported, and at least in some cases where the intramolecular nature has been ascribed to a conducted Tour mechanism, as you can see here. That is, you start with R joined to this allylic framework with base, then base gets attached to this allylic hydrogen, and this can be shifted to this terminal carbon, that is the other end of this allylic framework, and furthermore the base will be removed and the double bond which gets arise is at the rearranged position. Now, after the base catalyzed mechanism, let us try to understand the acid catalyzed mechanism in these rearrangements. Acid mediated two-step double bond migration has also been reported, and in this reaction first a proton is gained leading to formation of a carbocation, and then another proton is lost to form the double bond. So, let us look at these two steps as shown here. So, first step you can see here shown is the example of 1-butene which takes the proton, and you see this is the more stable secondary carbocation which is formed, and in the second step this secondary carbocation will undergo removal of proton, but this time it will give you the rearranged double bond, that is not at the initial 1 position but at the 2 position. So, from 1-butene we are getting this rearranged 2-butene or the isomeric product which is 2-butene. The acid catalyzed reactions are much less synthetically useful because of possible rearrangements of carbocation that gives rise to multiple side products. Therefore, wherever possible, mixtures of all possible isomers are usually obtained. After the base and acid catalyzed mechanism, let us now move to metal catalyzed mechanisms. Metal ions under homogeneous or heterogeneous conditions have been used to get isomerization of olefins under the electrophilic substitution conditions. Transition metal complexes such as platinum, rhodium or ruthenium or metal carbonyls are the commonly used ones. As with the case of base catalyzed methods, there are two mechanisms to bring about the shift in case of metal catalyzed ones. Out of these two methods, in the first method, it is the metal hydride addition elimination mechanism, which is, and in this mechanism an external proton is required, which is then abstracted from the substrate as shown in the mechanism here. So, we can see here the R joined to this allylic framework in the presence of metal hydride, that is MH. What happens is there will be addition of M and H to this double bond, and as a result we get this intermediate molecule, and then this undergoes removal of MH, but this time the removal will happen not where the addition has happened but to the adjacent position, and we get this new double bond at the rearranged position or at the isomeric position. And here again you can see the wavy bond with the R is representing that both the cis and trans double bonds or alkenes will be formed. Isomerization of 1-butene by rhodium 1 is an example of a reaction that takes place by the metal hydride mechanism, leading to 1,2 shift in double bond. If you look at the second method is called as pi-allyl complex mechanism, and this pi-allyl complex mechanism does not require external hydrogen and proceeds by hydrogen abstraction to form eta 3 pi-allyl complex, and this you can see in this visual as shown here, that R joined to this allylic framework of this alkene in the presence of metal here. The metal will bind to the double bond and you get this pi-allyl complex, and this pi-allyl complex undergoes rearrangement. You can see earlier it was between this carbon, it will further undergo removal, and what you get is a double bond which is attached to M with the rearranged position, and eventually the M will be lost and we get the isomeric or the rearranged alkene. And if you look at example for this, such a reaction when carried out on 3-ethyl 1-pentene with iron carbonyl catalyst, it will lead to 1,3 shift. As an example for the mechanism, a catalytic system to yield quantitative jet selective isomerization of N-allyl amides to Z enamides was found through in situ ruthenium based catalysis, and this you can see it is being represented by this equation, that here we are starting with CONH at this position where the double bond, notice that it is at the terminal position, and under these conditions of ruthenium based catalysis, and what we get is the double bond rearranges to this position, and this is now conjugated to the CONH system. That is, from N-allyl amide we have got this Z enamide. With metal carbonyl catalyst, the isomerization of 3-ethyl 1-pentene involves 1,3 shift, giving rise to 3-ethyl pent 2-ene, and this you can see as it is depicted in this visual. We start from 3-ethyl pent 1-ene in the presence of iron carbonyl, that is Fe3CO12. What we get is this iron carbonyl the metal will be bonding with the double bond through the pi allyl complex, and then this pi allyl complex, it will be furthermore getting rearranged, the double bond to this position with the metal still attached, and eventually this is lost, the M is removed, and then we get this rearranged product where the double bond has shifted to this particular bond, it is 3-ethyl pent 2-ene which is formed. A similar mechanism of double bond shift is possible for alkynes also, where the reaction proceeds with a carbanion alene as the intermediate, and this you can see in this mechanism, that is we start from this terminal pentyne, that is 1-pentyne, and when it is treated with base, the base will be taking out, notice that one of these propagylic hydrogen, and as a result we get C minus, and this C minus will be further undergoing resonance with the conjugated triple bond, and we get this cumulated alene type of framework where C minus is there, and then from base it will take this proton. So formed cumulated diene as the carbanion, this carbanion will act as a base, and from BH it will take the H plus, and as a result we get this particular alene. This alene will be further attacked by base and it will take out this proton. As a result we get this carbanion which again undergoes resonance, and we get triple bond at this position and carbanion at this position, and this resulting carbanion, which is the propagylic carbanion at the terminal carbon, now takes a proton from BH, regenerating the B minus, and that is how you get this 2 pentyne starting from 1 pentyne as the rearranged position of the triple bond. Let us consider another example when 1 hexyne isomerizes in DMSO with potassium tertiary butoxide as catalyst after 92 hours of reaction at 72 degrees centigrade, and in this case a mixture of products was obtained where among others the diene product predominated. So you can see here starting from this 1 hexyne, these are all the 4 different products that are formed, that is we get 2 hexyne which is around 10.2%, then we get 1,3-hexadiene which is around 2.3%, then we have the 2,4-hexadiene where E and Z configuration for the double bond is there which is around 52%, and then if we have both double bonds as E, that is EE24-hexadiene, then it is 34%. An indirect method of double bond isomerization leading to migration in the direction of terminal alkenes is also known. The method involves conversion of the alkene to a boron. The borane rearrangement followed by oxidation and hydrolysis leads to alcohol, which on dehydration forms the alkene. The driving force for the reaction is reversibility of reaction upon heating the borane, whereby equilibrium favors the formation of less sterically hindered borane, and you can see this reaction as shown here, that is we are starting from, this is the 3-hexene you can see, and when it is treated with BH3 borane, then this is the trialkyl borane that will get, you are already aware there will be addition of BH2 and H and eventually leading to this trialkyl borane, and when this is heated at the alkyl borane stage it is undergoing rearrangement, that is boron will get shifted from this carbon to this terminal carbon, and when this is subsequently treated with H2O2 in the presence of alkaline medium, then this boron will get hydrolyzed from here and in place you are getting OH, that is you get the corresponding alcohol. And this alcohol so obtained, which is, notice it is the terminal alcohol and not at the double bond position that we have started. When this alcohol is further treated with acid, it will undergo dehydration and now you are able to get the terminal alkene. And notice that this is of quite significance because preparation of more substitute alkene is more common via the CGF elimination, but preparation of terminal alkenes is comparatively difficult. So, this provides you a route to prepare the terminal alkenes via the starting from middle alkenes, that is you can isomerize the middle alkenes into terminal alkenes. Now, after this let us consider some examples of electrophilic substitution reactions which are accompanied by double bond shifts. To begin with, allyl silanes are found to be suitable substrates for electrophilic substitution reactions as they react with electrophiles with great regioselectivity. And you can see here the simplest mechanism for the substitution reaction is via the attack of the pi system. So, as you can see in this equation shown that here is the allyl silane, that is you can see at the allylic position there is SiMe3 group, and this allyl silane when it is attacked by electrophile, the double bond will be attacking on the electrophile and as a result adds this electrophile, there is a formation of this carbocation and the Cl minus will take this silyl group out and there is a formation of double bond here, and this double bond, notice that, is at the rearranged position, not at the earlier position there. And if you look at the mechanism, the simplest mechanism for the substitution reaction is via attack of the pi system on the electrophile, which generates a carbocation intermediate as and discussed just now, and this intermediate is then attacked by the nucleophile which displaces the silyl group forming the alkene. And you can see in terms of orbitals here, shown here is the allyl silane, and when this electrophile is attacking on the double bond, it is giving rise to a carbocation which has the vacant p orbital, and this vacant p orbital and this orbital where SiMe3 is there, the SiMe3 will be removed and there will be formation of double bond at this position. Since the loss of a silyl group is faster with oxygen and halogen nucleophile than the loss of a comparable proton, the position of the double bond is determined by atoms to which silicon is attached. Therefore, both the site of attachments of the electrophile and position of the new double bond are dictated by the silicon atom. For an enantiomerically pure substrate, the allyl silane gives one enantiomer of the product. This is because of the conformation of allyl ion which forces the proton on the silyl bearing stereogenic center to eclipse the alkene, so that the electrophile always attacks anti to silicon for both steric and stereoelectronic reasons. And let us look at this equation here, that starting from this E double bond and R for the stereo center where the silyl group is attached at the allylic carbon, when it is treated with tertiary butyl chloride in the presence of titanium chloride at minus 78 degrees centigrade, then the tertiary butyl group will be attacking on this double bond at this position and eventually leading to the removal of silyl group and formation of double bond at this. So, this double bond stereochemistry is E which is obtained. Similarly, when we look at its isomer, that is starting from ZR, that is earlier it was ER, now the double bond is Z here, and doing the same reaction, that is treating with tertiary butyl chloride the presence of titanium chloride, then what happens is the tertiary butyl will be attacking here, and you can notice the position of tertiary butyl, it will be attacking here because of the steric regions which will be opposite side, that is anti to silicon, and as a result there will be removal of the silyl group leading to the formation of double bond. And notice that this double bond is again at the rearranged position and the stereochemistry here is E. Let us take this example of this cyclohexyl, and there is a double bond at exocyclic position, and at allylic position you can notice there is a silyl group. So, when this molecule is reacted with alkyl halide in the presence of TiCl4, the R gets substituted at this position, that is on the cyclohexyl carbon, and the double bond gets shifted here as a removal of the silyl group, and this is obtained in almost 83 to 98% yield. If we do the reaction with CH3COCl in the presence of TiCl4, what happens is, here again you can notice the COCH3 is getting attached at this carbon and the double bond gets rearranged and with the removal of the silyl group. Similarly, when we do the reaction of this molecule with this epoxide in the presence of TiCl4, then this will be attacking on the double bond here and undergoing the ring opening. So, we have the attachment of this CH2CH2OH group, and the double bond in turn gets rearranged at this terminal position and again with the removal of the silyl group, and this is obtained in almost 87% yield. Similarly, if we do the reaction with this conjugated ketone, then this conjugated ketone again via the double bond will be attacking at this position, and you get this product in almost 55% yield. The same mechanism is operative as we have discussed earlier, except for the fact that the Lewis acid makes the electrophile more activated to be attacked by the double bond. So, again there, if we recall, the electrophile attacks the double bond which gets rearranged, and then there is the removal of the silyl group. So, let us now summarize what we have learnt in this module. We have learned that the double bond migration in allylic substrates can take place by electrophilic suction as well as nucleophilic suction. The double bond displacement take place via the SE1 mechanism, where first a carbon ion intermediate is generated, or it can also take place via the attack of double bond on the electrophile, which then proceeds through a carbocation intermediate. We have also studied that the kinetically controlled cis products will predominate due to the cis allyl geometry. The double bond rearrangement occurs to favor internal alkenes over the terminal alkenes. Conjugated alkenes are preferred over non-conjugated alkenes, and endo double bonds in cyclic systems are preferred as compared to the exocyclic double bonds. There are various methods of olefin rearrangements through base catalyzed, acid catalyzed or metal catalyzed mechanisms that we have discussed in detail. Alkynes undergo bond shifts through anionic alene intermediates, and we have discussed case for that also. At the end, we discuss about how allyl silanes give rise to stereospecific products.